This is section 1.9a, inverse functions. The inverse function undoes the function. That is, f inverse f of x equals x. Alright, so we've seen inverses a little bit before. We saw it a tiny bit when we were doing logarithmic and exponential functions. But we're going to go into more detail now, and also during the rest of the semester. So first of all, let's just make sure we understand the symbol. It looks like f to the negative 1 power, but it's not. And the way it's read is f inverse. Okay, so when you see that negative 1 exponent, in this context, it just means f inverse. Kind of like when we were doing matrices, and we put a little negative 1 exponent next to a matrix name. That meant the inverse of that matrix. All right, so an inverse function undoes a function. Okay, so think of it this way, like, you know how functions have inputs and outputs. Suppose that, I don't know, suppose that a car wash is a function, and the car is the input, the dirty car, so you put that dirty car into the car wash, and out comes a nice, clean, shiny car. So we have our input, we have our function, we have our output. Well, an inverse function undoes what the function did. Okay, so you could think of it this way. You've got that dirty car, put it through the car wash, out comes a nice clean car. Well, what happens if you put that nice clean car into another function, which is a dirtying function, and just like a big muddy field, and you go really fast through that muddy field, and people throw rotten eggs at your car, and so that would be an inverse function, because what you're going to end up with is just what you started with before you went into the car wash, which is a dirty car. So an inverse function undoes the function. And just continuing that analogy, you could think of the dirty car as your input. You could think of the car wash as your function. You could think of the clean car as your output from that function. And your inverse function would be that muddy field that you drive through. Okay, because it undoes what the function did. Okay, so that's how inverses work. An inverse function undoes the function. And so the way we'd read this is f inverse f of x equals x. The original function also undoes the inverse function. It works both ways. Okay, so like just as that muddy field would undo what the car wash did, well, the car wash will undo what the muddy field did. Okay, so the original function also undoes the inverse function. That is, f of f inverse x equals x. In other words, f of x and f inverse x are inverses of each other. Okay, one's the inverse of the other. An example, the inverse of f of x equals x cubed is f inverse x equals cube root x. Now let's see how one of these functions undoes the other, and that will illustrate how they are inverses of each other. F inverse f of x would be taking the cube root of x cubed. Okay, so if f inverse x is cube root x, well, what we're sticking in to that function instead of x is f of x, which is x cubed, so we have cube root of x cubed. Now, notice how this is kind of similar to what we were doing with composite functions, where instead of putting x into a function, you're putting f of x into it. And we're doing the same kind of process here. So we're putting f of x into f inverse x, and we get cube root x cubed, and that's just x. Conversely, we can also do f of f inverse x, and what you have there is, since f inverse x would be the inner function here, that's just cube root x. And then you're plugging that cube root x into the outer function, f of x equals x cubed, and so you have cube root x cubed, and that is simply x. Okay, so we see how these two functions undo each other, so they are inverses of each other. Another example, verify that the function g of x equals x plus 1 over 2 is the inverse of f of x equals 2x minus 1. Alright, so I'm going to walk you through this one just to help illustrate the concept of inverses. So the way that we prove that g of x and f of x are inverses of each other, in this case all we're asked to show is that the function g of x is the inverse of f of x. But we know from the last screen that if g of x is the inverse of f of x, well, then conversely, f of x is also the inverse of g of x. All right, so first let's prove that g of x is the inverse of f of x. So g of f of x should undo itself to x, right? G of x should undo f of x to just get x. Does it? Well, that's what we're going to prove here. What we have is if g of x is our outer function, and that outer function is x plus 1 over 2, instead of plugging in x into that function, we're going to plug in f of x, and f of x is 2x minus 1. Okay, so that's why we have this 2x minus 1 here. And then when we simplify all that, we're left with simply x. And therefore, we've shown that g of x is the inverse of f of x because g of x undoes f of x. The converse is also true. If g of x undoes f of x, well, f of x also undoes g of x. All right, so f of g of x would be 2x minus 1, but instead of putting x in there, we're putting g of x in there. And so we have 2 times the quantity x plus 1 over 2 minus 1. And then that all simplifies to x. All right, so we've shown that g undoes f and f undoes g. And therefore, g of x and f of x are inverses of each other. So it follows that g of x equals f inverse x and f of x equals g inverse x. The ordered pairs of the function f are reversed to produce the ordered pairs of the inverse function. Okay, you should write that down, and then on the rest of the screen we're going to illustrate what we mean by that. The ordered pairs of the function f are reversed to produce the ordered pairs of the inverse function. Now in the previous example, f of x and g of x are inverses of each other. We already showed that. If any ordered pair is on the graph of f of x, then the reversed ordered pair must be on the graph of g of x. That is simply restating what the first sentence on the top of this screen says. And now let's look at it in action on a graph. On this graph we see two functions, and those two functions are the functions from the last screen. F of x equals 2x minus 1, g of x equals x plus 1 over 2, and as we saw on the last screen, f of x and g of x are inverses of each other. And so now we're just going to examine a property of inverses that we can see with these ordered pairs that I labeled here. Okay, so here's one ordered pair, 3, 2. The point 3, 2 is on the graph of g of x. Well, since f of x is the inverse of g of x, then it has the point 2, 3. Because since these are inverses, the x's and y's get swapped. All right, likewise, we have the point 5, 3. The point 5, 3 is on the graph of g of x. And since f of x is the inverse of g of x, it has the point 3, 5. All right, so this is just a property of inverses, is that the ordered pairs are swapped. And this property brings us to another one, which really is just a consequence of it, is that the graphs of a function and its inverse are reflections in the line y equals x. They're reflections in the line y equals x because when you have a swapping of x and y coordinates, as we have with these ordered pairs, the pattern it creates is it uses the line y equals x as an axis of symmetry, because that's the line around which these coordinates are swapped. Okay, so you just need to remember that when you have inverse functions and they're both graphed on the same set of axes, they will be symmetric about the line y equals x, precisely because the ordered pairs are swapped. The ordered pairs are swapped. The x on one graph is the y on the other, and the y on one graph is the x on the other. The domain and range of the function f are reversed to produce the domain and range of the inverse function. Okay, this is another property of inverse functions. An example, for the function f of x equals e to the x. Remember, that's the exponential function. We learned that in chapter 3. So f of x equals e to the x. The domain is negative infinity to positive infinity, and the range is 0 to infinity. The inverse function f inverse x equals ln x, natural log x. That's the logarithmic function. Its domain is 0 to infinity, and its range is negative infinity to positive infinity. Now, this is a graph just to refresh our memory, since Chapter 3 was kind of a long time ago, although you did study it for the final. But we have f of x equals e to the x. That's one graph here. And the inverse of f of x is the logarithmic function, so that's ln x. And we see that the domains and ranges are swapped, right? So if we look at the domain of f of x, just graphically, we can see that the domain of f of x is from negative infinity to positive infinity. It's all real numbers. There's no number that you cannot plug in for x. Therefore, the domain is all real numbers. Now the range of f of x, that's where we look at all the different y-coordinates for the graph of f of x. And we see that those y-coordinates range from 0 to infinity, and not including 0, of course. Now, because of limitations in graphing, it appears that the graph of e to the x touches the x-axis, but it doesn't. The x-axis is an asymptote. So even though the graph of e to the x approaches the x-axis, it never actually touches it, because 0 is not actually part of the range of the function e to the x. And that makes sense, because if you raise the number e to any exponent, there's no way that you can get 0. There's no way that you can get 0. You can only get positive numbers, and you cannot get 0. That's just the nature of exponents. Now let's look at the graph of the inverse of f of x, which is ln x, the natural logarithmic function. And notice that the domain of ln x is the same as the range of e to the x. And the range of ln x is the same as the domain of e to the x. That's another property of inverses, which is really just a consequence of the fact that x's and y's are swapped, which is also related to the fact that the graphs are symmetric about the line y equals x. All of these properties are related to each other. Okay. Now let's look then at the domain and range of ln x. Well, looking at the domain, all the different possible x coordinates, all the different possible x values that we can plug into this function, that goes from 0 to positive infinity. But all the different possible y values would be from negative infinity to positive infinity. Now, a lot of times students see this ln x graph and see how it kind of flattens out. But the fact is that even though it doesn't increase by a lot as you go to the right, it's still increasing. And when you go to infinity, it's just still increasing. So there is no limit to the range, and the range is all real numbers. Notice how the range of one is the domain of the other, and the domain of one is the range of the other. So the domain of the inverse function is the range of the original function. The range of the inverse function is the domain of the original function. And as we saw in the last screen, the graphs of a function and its inverse are reflections in the line y equals x. And we can see that here. You can clearly see that if you folded the graph over using the line y equals x as a crease, you would have it lined up perfectly, because it's totally symmetric about the line y equals x. And we would call y equals x the axis of symmetry in this case. Just a little graphic illustration of the sets, because remember, with sets you can have Venn diagrams, and drawing them as circles helps. That's something that the whole concept of sets is something that you learn in Algebra 1. It's easy to forget with time, but it still has a lot of applications, and sometimes the best way to visualize what's going on is drawing circles. All right, so the domain of f is any x that we can plug in, into f of x, and the range of f is any value that's possible for f of x. And notice that the domain of f is the same as the range of f inverse, and the range of f is the same as the domain of f inverse. And f of x is x plus 4, f inverse x is x minus 4. It's pretty simple to see how one undoes the other. Like, you can test right now. Try plugging x minus 4 into f of x, and that x minus 4 would replace your x there, and you just, have x minus 4 plus 4, so all you end up with is x. The same is true if you plug in x plus 4 into f inverse x. Let's say that we just took this x plus 4 here, and we use that x plus 4 to plug in for my x here, and I would just end up with x plus 4 minus 4, and that's just x. Right, so it's pretty easy to see that f of x and f inverse x here undo each other. The classwork, page 99, write these numbers down, and we'll work on them in class.